Dr. Lippman.
Yep, I remember.
Okay.
All right, so the question was how would I have handled the stopping the rat from moving around as a dead corpse? Is that the question?
Correct.
So let's that was our grid one, right? I already have that. Oh, I already have it in here. Okay. So let's look at that first, and then we'll go and look at finishing the game of life from last time. All right, so let me just see what this guy currently does. Was the rat doing anything? Do I not have, oh, I don't have any of that stuff in here. Oh, that's right, because we wrote it, my interpreter wasn't working, so I wrote it in a different thing. No problem. Let's go into Slack here. Yeah, I'll tell you what, this thing scrolls really, really fast. All right. I just need to bring this into our, all right, call that good. So do I need to save it? Let me just get it to the point where the rat's moving around again. Should. Oh yeah, he's moving now, just a little bit slow. All right, so we want to have it when we attack this rat. Do I know where he is right now? Well, wherever he is. When we kill him, we want him to stop moving. So once he enters into a death match, the starting point is going to be once he enters into a death match, we need to be able to tell that NPC to stop moving to begin with. So we don't want to have a rat running rampant during a fight, you know, where you're in the middle of a death match. And since the two objects are already in that deathmatch object, they'll continue to fight even if they're not in the same room. You know, even though to us that doesn't make sense. You know, like, okay, well, the rat ran away, we're not going to continue fighting. Well, because we have pointers to both the player and the inhabitant, the rat, inside of our deathmatch object, they're going to just keep fighting regardless of where they are in our world. So right when a fight starts, we want to go ahead and stop that movement anyways. So let's see how we started that movement. We told the NPC to come alive. And let's see. So the target was self.move. So this is our function right here where the rat keeps moving. All right. What I'm going to do is in my NPC, so I think this is kind of what you were asking, Ben, is how do you pull this off? Well, I'm going to have my NPC keep track of a variable called should move. Self dot should move, and we'll set that equal to true. So in here, we'll say while self dot should move, do this. All right. Now, what'll happen here is each time through this, let's see, where are we taking our break? We're sleeping between 5 and 15 seconds. And what I'm going to do is, well, this is fine. We'll leave it like this. There will be that possibility of there being this thing called a race condition where we actually are in the we type kill, and in the moment that a death match is starting, since a thread is running separately, it will potentially have that rat move again, because he would have woken up, he would have gone down through this stuff, and then he would have detected that, oh, I should, you know, I should go ahead and move.
That's actually what happened every time until we put like another if statement with inside of it before the sleep function.
Well, we can do this anyway, because I think we can say a thread stop. Is that a thing? Stop's not a thing. Okay. I guess we would have had, we could do this if self dot should move do that stuff. That way, if it happens, if we get in here, but sometime during this 5 to 15 seconds, we switch it, we still will test it again. And we'll only actually potentially move if should move is still true. Now, for those of you who maybe are a little confused by this is the same thing as saying equal true. Remember, a Boolean expression is any expression that boils down to a single value of true or false. So self.should move is already a value that will be either true or false. So I don't have to ask, is true equal to true? It's already true. It's already itself. So while this isn't wrong, it's redundant. This is like saying if 5 is equal to 5. 5 is always equal to 5. All right, so if self dot should move, do this stuff. So that'll protect us from this gap in here where we might, in that 5 to 15 seconds, we might have started a fight. Something like that. So now what we'll do is inside of Deathmatch, where's my Deathmatch? Actually, we can do it on the kill command. Oh, we don't have our kill command in here, so we have to put our kill command back in. That was from a different, so we have this thing kind of in piecemeal right now. Do I at least have deathmatch object written here? All right, I do. So deathmatch has a player and an NPC, and so before we, and then we tell them to start their fight. All right. So I'll come back down here and we'll just change up our menu a little bit to allow us to potentially type in kill. So instead of saying what direction do you want to go, we'll just update our thing and say, what do you want to do? And we'll go ahead and read in the command here. So what do you want to do? And we'll go ahead and ask the question, if command is equal to kill. Now actually, command currently has, it would be something like kill rat. So we really want to say if we want to split that guy. Let me stop this. Kill rat dot split. Won't that just do it on spaces? Yeah. If I just say east dot split, that just gives me east. Okay. So after we have command there, we'll say command list is equal to command dot split, and that'll get it into a list for us. And then we could say if command at bucket 0 is equal to kill, then we'll go ahead and we'll create a deathmatch. And deathmatch took in, was it the player and then the NPC?
Yep. And then use a capital M in deathmatch as well.
Okay, thank you. Player, then the NPC. So we already have our player is called the Inhabitant. And they're going to be fighting against some bad guy. Okay, and we're going to have to ask the current room for us to find. So a room should have the ability to find an inhabitant. So here's a room. Okay, we didn't, well, we did write it. We just haven't written it in this code. So we have the ability to, we have a list of inhabitants in a room. We want to find the inhabitant that has a name equal to something and give that to them. So we'll go ahead and we'll just write it up here. Find inhabitant. And I think this is all stuff we had previously written, just there was that week where I just updated my operating system and couldn't write it in here. So I think we did some stuff online and things like that. So we have code floating around. So find inhabitant. This guy will take in that and then a name. And we're going to go ahead and go through for inhabitant in self.list of inhabitants. If inhabitant.name is equal to name, if I found the guy, then we'll return inhabitant, the guy we found. If I go through all my inhabitants and never find it, I'll go ahead and return none. Didn't find him. So now I have the ability to find an inhabitant inside of a room given the inhabitant's name, and he'll either return for me a real inhabitant or he'll return for me nothing. So if we said kill, we want to go ahead and say who to kill is equal to the inhabitant dot what's it, current room dot find inhabitant command at bucket 1, because that's going to be the name of our inhabitant. If you see down here, I gave like a sample of what our command might look like. Yeah, this is like unusable, the scroll. So if I say kill space rat and I split that, bucket 0 will be kill, bucket 1 will be the name of the thing I want to kill. Okay, so that's what this bucket 1 is. So who to kill, the inhabitant, current room, find inhabitant, who I want to kill. Then I'm going to say if who to kill is not equal to none, if it's a real thing, then we'll go ahead and start a match between the inhabitant and who to kill. Okay, now who to kill, for right now, we can assume, since we only have one inhabitant in the world, we can assume that this guy is a NPC. So before we start this fight, we want him to not be able to run away. So we'll say who to kill dot should. Oh, we don't necessarily know he's an NPC. Didn't I say should move? Should move is equal to false. That'll keep him from moving from this point forward until, if he lives, well, we'll assume he dies for this case, but this will keep him from moving. So this will stop his thread from continuing to make him move. The thread's still running. It's going to keep checking every 5 to 15 seconds if he's allowed to move yet. So you've kind of like hit him with a freeze ray. All right, so this will stop him from moving. We'll go ahead and have the fight. What's the start thing? Is it dot fight? So the fight dot fight. So we'll tell them the fight. Somebody lives or dies there. So after this fight is over, we'll go ahead and ask if who to kill dot HP. Although, did we create like a is alive? If who to kill dot HP is greater than 0, then we can go ahead and say who to kill dot should move can be equal to true. So if he somehow survives the fight, we'll let him start moving again. Okay, so that's what we do in the event of a kill command. So if in a kill command, we get who he's supposed to kill, as long as it's a real thing that's here. So if I say, kill pumpkin, and there isn't a pumpkin in the room, this guy who to kill will come back as none. So I won't get into this if statement, and it'll just go back through and ask me what I want to do again. All right. So I could even do an else to this if I want to. I could say else print they are not here. Something like that, letting me know that if I said kill pumpkin, they're going to say that person is not here. I can even do this. Command at bucket 1 is not here. So that'll say, pumpkin is not here. So that'll be my else to that. So if the person I'm trying to kill is here, go ahead and make him stop moving, create a death match, start the fight. If he lived, go ahead and let him start moving again. Otherwise, he's never going to start moving again because I'll never flip his should move back to true. Let's actually think about that for a second. The reality is once I set his should move to false, he'll never actually start moving again. So we'll address that in a second. Flipping it back to true here actually will make it so that he would be allowed to keep going, but he actually isn't moving yet, because if I go up and I show you NPC here, we can do it through come alive. Notice here that move keeps going as long as should move is true. As soon as I flip this guy to false, the next time through this loop, this will be false, will fall to the end of move, and he'll be dead. He won't be able to move again. So just flipping this variable back won't make him move again, because this function has now completely ended. So what I'll have to do is I'll have to tell him to come back alive. So I can switch it back to true, but then I can say who to kill dot come alive. And that'll make a new thread and have him start potentially moving around again. All right. So if it's a real thing, stop him from moving, fight him, check to see if he's still alive. If he is, allow him to move again, then actually start up the thread. Start his engine again, so to speak. All right, so that's what we'll do, is if the command is equal to kill, else we'll assume the command is a exit like we had before.
So then will we have two threads running then?
No, because the first thread died when that function ended. When that move function ran to completion, that thread ended.
Okay.
Before that, when we had it while true, that function never completed, right? It just kept spinning forever. So that thread was continually going. But as soon as we flipped this guy to false, the next iteration through that loop, that thread ended because the move function ended. So this will start that thread back up. All right, and then, so if it's not a kill command, it's one of these other things. So we should be good to go here. So we'll let the rat move once. Direction is not defined. Oh, because it's not called direction. Remember, I changed it to command. This is command at bucket 0 would be the direction we're asking them to move. It used to just be called direction. I'll go ahead and type in north here in preparation for him to move to the north. All right, let's move to the north. Ay, ay, ay. Oh, ay. Also command at bucket 0. Although this should have been a real exit. Find exit. Kill rat. All right, so hold on. My split is just getting me a K. So I read, oh, it's called command list, not command. Sorry about that. Command list, command list, command list. Because command is just the string that I read in. Command list is the actual. All right, so I should be able to go to the north now. Rat leaves to the north. Kill rat. Not getting into kill. Just make sure I'm getting in the kill command. Okay, I did. I fought him. And we'll see now that he's not going to move. I'm still not sure why it didn't work when I moved him. I'll go to the north here. Kill rat. Okay. It was just off the screen. That's why I couldn't tell it did it. Why is he still moving? Oh, the rat was victorious.
You died, yeah.
So there we go, my hero. So our rat is still alive. And I don't have any way of regenerating my hit points. So now this rat will just roam free forever. So let's try this again. We'll let him go to the north. Then I'll kill rat. All right, so I'm victorious now. So this rat shouldn't do any more moving. And we just saw in the previous example that he did start moving again after I killed him. So something along those lines would accomplish this. Does that make some sense?
Yeah, we were thinking that it had something to do with the sleep function, why he would still move once, and we couldn't. I mean, we used an if statement to stop it from working, but we felt like that might have been like redundant or something like that, because the
Yeah.
while loop is asking the question already if his life state equals, or I mean, you use should move. If it says should move is true, then do this. But I just thought it was weird how the sleep function messed with it.
Right. Yeah. So this is actually an operating system concept, although this is super obvious in this example. So in operating systems, we have this thing called a race condition where, when computers are really, really fast. So when you have all these things happening in your operating system, all seemingly at the same time, it's potentially possible that two things kind of try to happen at the identical period of time. In fact, we have all sorts of tools in operating systems. One of them is called a semaphore that allows you to kind of control access to a resource to make sure that two people don't accidentally grab the same resource at the same time because they both kind of got there at the identical time. This case, it's a little bit more obvious because, well, it's a little bit more likely to occur in our case here because we're not talking about, the random amount of time being in nanoseconds, right? We're thinking the random amount of time is between 5 and 15 seconds. So if after we got past this gate, if in some time in the next 5 to 15 seconds, that person should move gets flipped to false, we would have still had him move one more time. So that's why we protect it in here. The other thing you could have done is you could have had him, you could have done the sleep before the first time. So you could have moved this in here, done a sleep. Oh, this is weird spacing. Then we would have, we could have done this as a do while loop. Yeah, whatever. And then we would have the same line again. So sleep once at the very beginning, then let them go. Do it, sleep again. So this would be the one gate we would need to make it work. Does that make some sense? So then you could have done it with a single, you wouldn't have had to add the extra if statement in there.
Sweet.
Okay. Here, let's make sure this guy still does what we want it to do. All right, so I won, so he's not going to do any more moving. Okay, so I'll go ahead and paste that code. Let's see. Threaded kill rat, something like that. Okay. And then let me go back and see if I have in our keynote, we have the rules for Game of Life. Okay, well, I'll go ahead and bring them up in a browser then. We'll review those rules. Conway, Game of Life. Okay, so any live cell, if the cell is currently live with 2 or 3 neighbors, it survives. So what we need to do is each time through, we need to create a copy of our grid, because if we start making changes to the original, then we are, each time we try to find out how many new neighbors they have, or how many live neighbors they have, it's going to be off because things are changing. So we need to work with the copy for making decisions about what the next state of the grid is going to be. So we'll always look at the copy and look at a individual bucket and see how many neighbors, how many live neighbors does this guy have. And then when we make a decision about what should happen the next round, we make the change in the original, not the copy. Okay, so if a live cell currently has 2 or 3 live neighbors, he's going to survive in the next iteration. If a dead cell has 3 live neighbors, it'll become a live cell. So if it has exactly 3 neighbors and he's currently dead, he becomes living. Otherwise, they stay in their current state. All right, so those are the rules that we need to apply. And that's what we did in here. And just to kind of review our code to bring us back up to speed, remember our grid is going to be a list, and it's going to be a list containing lists, where it's going to be a grid is going to be a collection of rows, and each one of those rows is going to have a list with some number of columns. All right, and we'll go ahead and fill this guy up with random spaces and asterisks to give us our current grid position, our grid view. All right, I'm going to come back to that update because I actually wrote this already, just for the sake of time. So we'll go and say get copy of the grid. So I mean, really, from last time to today, this is all we really needed to change. So it's not like I wrote a bunch of code. All right, so we gave ourselves the ability to get a copy of the current grid, which says, you know, whatever the current state is, here's a duplicate of it, an entire duplicate, not another pointer to the same thing. Because remember, arrays or lists are passed by reference. So if I just said get copy of it and then I returned the exact same, I just said return the grid, I would be returning another variable that pointed to the identical place in memory. That means that anytime I change something, if I change bucket 00, it would be a real change, permanent, and then it would affect my rules being applied moving forward. So I want to get a completely separate grid. So I'm going to start with an empty grid. I'm going to go through it. I'm just going to make a duplicate of everything that was in the original. Okay, I'm just literally copying every single value to build a grid copy. All right, so now I have two separate grids that look identical, but they are in different places in memory. All right, grid knows how to display itself, just makes it look pretty on the screen, whatever. All right, then we have our game of life thread. Game of life thread first creates a grid. So we're doing an 8x30 grid. Okay, then it says forever, while true, go ahead and display the grid. Then we're going to apply our rules. Okay, our apply our rules says get a copy of the grid. Then we're going to go through every single row and column in the grid, and we're going to ask how many neighbors does the current row and column have in the grid copy, knowing that we're going to be changing the real grid, not the grid copy. So how many rows, how many living neighbors does the grid copy have given its current row and current column, which we're looping through for all the rows and columns. So we're going to get a number with that. This is the number of living neighbors. Then we're going to call update. So now we're going to apply these rules. So this update function is what we didn't write last time. This is that one piece. Let's go up to that update function. So here's update. It takes in a row, a column, and a number of neighbors. And we are updating the original grid, not the copy. All right. So first, we go ahead and we grab whether or not the row and column that was passed in is currently alive. It's alive if we have an asterisk there. Then we ask if it's alive, and this is a Boolean expression right here. The number of neighbors is less than 2 or it's greater than 3. Okay, which means it's not exactly 2 or 3. Remember, if it's alive and it has 2 or 3 neighbors, it stays alive. So this is saying if it's alive and it has less than 2 or it has greater than 3 neighbors, it will die in the next iteration. We'll change the asterisk to a space. Else if it's not currently alive and the number of neighbors is exactly 3, it'll go from dead to living. If a cell is alive and it has 2 or 3 live neighbors, it remains alive. So we don't need to do anything to that guy. So our first rule says if it's alive and it has less than 2 or greater than 3, kill it. That's what that first if statement says. If it's alive and it has less than 2 or greater than 3 living neighbors, kill it. If it's alive, less than 2 or greater than 3, kill it. If it's dead and it has exactly 3 living neighbors, make it alive. If it's not alive and it has exactly 3 neighbors, change it to alive. Otherwise, we just leave it alone. If it used to be alive, it stays alive. And if it used to be dead, it stays dead. All right, so that is our update method that applies the rules of the game of life. So again, what do? We get a copy of it. We go through every single row and column. We get the number of neighbors for a particular row and column. And then we ask the original grid to update himself, given that row, given that column, and the number of neighbors. Then we have them sleep for a half a second. We clear the screen and he goes at it again. Let's see what this looks like. All right, so that now we're stuck. This population is not going to go anywhere else. All right, so that is the game of life. And if we want to see if we get a little bit longer running thing here. And there's modifications on the game of life where you could have more than, either a living or dead. You could have multiple different life forms where different life forms play by different rules. Like, you can have predators and prey, that kind of stuff. So again, hopefully this gives you some reasonable uses for threads, and you kind of see how we can kind of make our programs feel somewhat alive, even without graphic user interfaces or animations, things like that. All right, that's where that guy died out there. And we probably could put in something that says, if the state of the grid doesn't change for, 2 iterations in a row or something like that, then just kill off our thread. So make it exit, do something similar to what we just did so it doesn't just keep pulsing like this. But effectively right now, we're applying the same rules every single time and nothing's ever going to happen. All right, so questions about that. That's what we wrote last class before break, and had everything done except the update. I'll go ahead and give you that code. Okay, let me go back in here. All right, so what we're going to do now is we're going to talk about databases, but we're going to talk about it at the high level. If we have a little bit of time, the end of next class, actually, let me think about this. Are we doing on time? 5 to 11:20. Let me do this instead for right now. Let me go through the slides. I'm going to tell you what I think are the important things to study for the final exam. What I'll have for the final exam will be, the exam will be up by like Sunday night at some point on Blackboard. I just need you to get it done by midnight on Friday. So anytime during finals week, you can complete that exam online. I'm going to design the exam to take about an hour. I'll probably put the time limit on it at 2.5 hours or something like that. So it should not be a time crunch situation. I want to see what you're able to do. I'm going to tell you, don't Google stuff, don't cheat. You're only hurting yourself. If you're really stuck on a question and you just don't know what I'm asking and you need to just glance at your notes to kind of remind yourself of something, I'm okay with that. Because I want you to show me what you're capable of doing, not the stress of finals week and stuff like that showing up where you just forgot something. So, don't cheat, but if you need to kind of, refresh your memory, which would be kind of equivalent to maybe you coming up to me during an exam and saying, what are you asking here? And I kind of give you a hint. It would be something similar to that. I think that's reasonable. So just use your best judgment and don't cheat, but make sure you're showing me what you've actually learned in the class. So what I'll do is so that'll be up. You'll have the entire week to do it, but you have to do it in one sitting. You can't do it in pieces. So once you sit down, make sure you have a couple of hours to finish it, even though I'm to design it to take 1 hour, and then get that exam submitted. I'll be around all week if you have questions in studying or anything like that. So what I'm going to do right now is I'm going to go through the slides and kind of point out the things that I think are most important to focus on for the exam. The exam will focus on the stuff since midterm, but it will still potentially have stuff that was on it before the midterm. Okay. Because it is a cumulative exam and you should know all this stuff at this point. A lot of the stuff before the midterm is just building blocks for stuff after the midterm. And then what we can do is on Wednesday, if you have questions, you have something you want me to review in code, we can spend some time on Wednesday doing that. And then once we're done with that, I'll introduce databases, because that's something we'll be messing with some next semester, but it'll also give you kind of a contextual idea how they fit into programming. All right, so let me bounce back. All right, so let's look at what we've done since the midterm first. And then we will, you know, because the midterm has mostly been about object-oriented programming. We've done it in the context of really one big project and or a couple of kind of piecemeal type things. All right, so, you know, since the midterm, we focused on object-oriented programming. So the implication there is for what to study for the homework, you should be able to create simple objects. And what I mean by that is if we go back in here, you know, if on the exam, you know, let's say I said, create a class called grid that should keep track of a number of rows and a number of columns, and it should maintain a list of strings, something like that. Or similarly over here, like a room, you know, create an object called room that has a name, and a room has a name, a list of exits, and a list of inhabitants. All right, so this guy is an object that is storing some pieces of information about a room. Okay, so this whole idea of creating objects and then making those objects do things. So, you know, I might say then, you know, create a method within that object to find an inhabitant given that inhabitant's name. So you would go through all of your inhabitants inside your list of inhabitants. Each time say, am I looking at the guy with the right name? If I am, return him. All right, so you should be able to work with objects a lot on the final exam. So you really need to show that you understand how objects work, which is pulling together the stuff before the midterm. Okay. Also in context, notice we have several different kinds of objects in here. So we have a room object, we have a dice object, a deathmatch object, an inhabitant. Now within inhabitant and NPC and player, notice that we have an inheritance model. An inhabitant is a top level object where player and NPC are built in terms of inhabitant. Okay, so you should understand how inheritance works. Specifically, the self keyword versus the super keyword. Know what those guys are and how to use them. All right, so let me go back into here. All right, so understand that we created this picture. We said we want to come up with a way of representing the department. So it would be fair game for me to give you something simpler than this, but maybe a little scenario where but if we're playing off of this, we'll say, okay, here's the scenario. We want to come up with some way of representing the computer science suite at the school. Okay, the computer science suite at the school is made up of a collection of rooms. We even treated the big long hallway as a bunch of rooms. Okay, so we decided, okay, we're going to do this as rooms on a grid. And what links those rooms to each other? These little exits. So this is an object. This is an object. All right. And then who goes into this environment? Well, we have our inhabitant. He's the guy that originally can run through there. All right. So in this picture right here, we've depicted 3 different objects that need to be created. A room object, where a room has a name and it has a collection of exits, and it probably also is going to have a collection of inhabitants. Remember the first version of this we wrote it to only have a single inhabitant. We didn't have rats and stuff like that running around. So, this guy just has a single inhabitant. So we say room is a name, a list of exits, and a list of inhabitants. An exit is a link between 2 rooms. So an exit will hold a room A and a room B where you're going for that. Or it could just hold a single room that is the destination room. So you can kind of decide, how am I going to implement exit? Is this exit right here, does it exist one time and both of these rooms have that exit? Or does this guy actually exist twice? Is there an exit going from R1 to R7 and then another exit going from R7 to R1? Either one is okay. You just have to create your object with that in mind. If you're going to have it only existing once, well, if you're going to have it existing more than once, you would say that an exit has a destination room. So this room here has an exit in it that has a destination to the north to here. If you're going to say that this exit actually links 2 rooms, you're going to say that it links R7 to the north and R1 to the south. And then when you take an exit, you would have to tell it, where am I coming from? So it knew which direction you needed to go. You would go to the other direction, away from where you were coming from. Okay, so I think we wrote it as separate exits where it just had a destination. Let me come over here to my exit. Yeah, so it has a direction and it has the destination where it's going. So if we were to connect this to our picture here, the reality is that there's actually 2 exits right here. One that leads from R1 to R7 and another one that leads from R7 to R1. All right. Again, that was dealer's choice. The programmer gets to decide how they want to represent that, and then they just write the code that makes it true. Okay, so again, if I give you some scenario, you should be able to tell me what objects would need to be created. And I would give you, again, a simpler scenario than this, but you would tell me the objects that need to be created, as well as the attributes each of them should have. So kind of like this, we can imagine, what does a room have in it? So if I say, here's a room should maintain a name, a list of exits, and a current inhabitant. You should be able to create a room class with an appropriate constructor for that guy. All right, so this is certainly be able to work with random numbers. I think we worked with those before the midterm anyways, but random numbers should be something you're comfortable with. And if you go and look at these code examples, I know a lot of them we didn't necessarily write in class. We wrote things that were in the spirit of these in class. Make sure you can follow these things. So I give you some examples of using a single person, doing some stuff with that. Be familiar with F strings. be able to work with lists and dictionaries. Remember that lists and dictionaries are passed by reference, not by value. So if you make a change to them, that change is permanent. That's the reason why we use the copy of the grid in our game of life. Understand the concept of instances of an object. You know, this guy, class person, is a blueprint. It gives us the directions for how to make an object. Once we actually create a person like we're doing right here, and in this case, we're appending it to our list of persons, but once we actually create a person, we are creating a single instance of that class. So in this case, we have two different, well, we have, I think we have 10 persons we've created. So we filled up this list of persons with 10 different person instances. And we're asking two of them here to print to get their full name, which would be their first name and their last name. Get full name is this function right here. Okay, and we should know that the person that lives at bucket 2 is going to likely give us a different name than the person who lives at bucket 5. They are different instances of the person class. All right. Just more examples with this. Again, another thing that's important to remember between well, for functions is whether a function prints a value or returns a value. Okay, that was something that was missed pretty often on the midterms. Okay, when an object, when a method returns a value, nothing necessarily shows up on the screen, only if whoever captured the value that was returned does something with it. When it prints a value, that makes something show up on the screen, but it does not provide a value to anybody else who called that function. So there's a distinct difference between printing a value and returning a value. Okay, this is the same thing I just said. Said a few minutes ago. Lists and dictionaries are passed by address. Strings, numbers, and other primitive types are passed by value. So make sure you understand that difference between something being passed by address, meaning that if we pass it and make changes to it, those changes are permanent. I used the example in class, probably if I gave you the address of my house and you spray painted my garage, when I got home, I would be in for a surprise because I didn't give you a copy of my house. I gave you the place where you can find it in memory, and then any changes you make to it would be permanent. As opposed to if I gave you a quarter, okay, let's say I had a quarter in my pocket, I was some kind of magician, I can make duplicates of the quarter, and I handed you a quarter, you would now have a copy of that quarter. If you made changes to that quarter, it would not impact the quarter I still have in my pocket. Okay, those guys are separate kinds of objects. All right, so inheritance. I probably won't test you heavily on inheritance, but I will. There will be at least one question that will have you grapple with, the role of inheritance. Whether it's the. I'll probably also want you to prove that you know the super keyword. I might give you that in the form of, here's some code, tell me what it does, and I might use the super keyword in the code. So you should know that the super keyword refers to an instance of an object's parent, whoever it inherited from. So like we've used the super keyword over here in our player. A player is built in terms of an inhabitant. So a player first called upon his parents' constructor. So this is calling his parents init method, passing it the name, and it created a generic inhabitant for it. Then we rolled the stats for a player and decided players are a little bit more powerful than NPCs. And you'll see the difference here inside of our NPC constructor. Again, we build an NPC in terms of our parent's constructor. And then we roll stats and we decide, oh, this guy's a little bit weaker. That's why the constructor for NPC basically builds a normal inhabitant, but makes himself a little bit weaker because we decided NPCs are weaker than players in general. But now NPCs also further differentiate themselves like we did today because they're going to have a mind of their own AI, so to speak. This is a pretty wimpy AI, but it's still an AI. So he's going to have whether or not he's allowed to move, and then he does some other things in his logic. All right. So definitely understand the concept of inheritance, the idea of having a base class and then two classes that have a lot in common with that base class, but then further differentiate themselves. It doesn't have to just be two classes. It could be 5 classes that all are based off of, you could have something called an automobile. And off of an automobile, you could have motorcycles, cars, trucks, vans, semis, all sorts of things, because all of those are automobiles, but they differentiate themselves in some way. Again, understand the super keyword. Here's that example I just gave. You have all objects in Python come from the generic top level object. Then from there, we built an automobile that I have it in yellow here, where the whole idea of automobiles is nowhere does an automobile exist. We have a lot of things that are automobiles, but the idea of a generic automobile really is not found in the wild. What we see in the wild are cars and SUVs and motorcycles and trucks. Those are the things we actually see in real life. Okay, so that's where the inheritance model comes in. Another example you can think of is like a coin. Okay, so I used the example a few minutes ago about quarters. So a quarter is a coin. So is a penny. So is a dime. So is a nickel. These are all coins. Okay, so we have this concept of a coin, and then off of coin we have some special versions of coins where a quarter has a value. It has a size, let's say, because the diameter of a quarter is bigger than the diameter of a dime, for example. So things like that, that special kinds of coins differentiate themselves by the core coinness of them. But when I say find a coin in a pile of stuff, you kind of know what you're looking for because you think that you know that coins look a certain way, even though they come in different sizes. All right, so there's an example here of an inheritance model with, that basically implements this. Goal of object-oriented programming, minimize the duplication of code. If you're going to write the same code inside of 2 different objects, you might question whether or not you should actually do that through inheritance. For example, in our player example back here, it was Inhabitant that could roll stats. This is inside of Inhabitant. An Inhabitant knows how to roll their stats given a max HP, max AC, and max strength. Then we used that from within player and NPC. We called our parents roll stats function to do something different potentially than, so we did 8, 8, and 2 for this guy, and then for player we did something higher, 15, 12, and 3 for players. Okay, so we still use that core ability that all inhabitants can roll their own stats, but certain inhabitants might have different levels of stats than other inhabitants. Be able to work with algorithms similar to like what we did in Deathmatch, where there's like this back and forth type thing and you keep going till some event occurs. So in Deathmatch, we decided that the player gets to go first because they're the ones who tried to kill the rat in our example. And then they just go back and forth until somebody dies. So understand how to create algorithms given a set of instructions like that. So basically the stuff we've done for our homework assignments. We only talked about MUDs because that's kind of what we are representing with our world. I'm not asking you anything about those. The idea of blocking versus non-blocking code. This is where we got into our introduction of threads and when you would use a thread and when you might not use a thread. So I might give you a scenario and ask you to tell me, would a thread make sense here? Why or why not? Something like that. You know, ask you to defend your answer in some way. Remember, blocking code is code that keeps you from continuing on in the program until it completes. So for instance, in our deathmatch, our fight is blocking code. So that just keeps running until somebody dies. All right. And nothing else outside of that keeps running unless we put it inside of a thread and started it beforehand. So blocking code prevents any other code from executing. Whereas a thread allows us to have stuff happening separately from our current thread of execution, where things that block only things within that particular thread. It doesn't block things in other threads that are currently executing. We talked about the concept of multiprocessing. This would be more of an operating systems or computer architecture type of question, more operating systems probably. So I wouldn't ask you questions on the exam specifically about multiprocessing. Your questions would be more about the tool that is a thread that allows you to get around blocking code or having, you know, multiple things happening at once, that kind of thing. So the applied side of this instead of the theory underneath it. The theory will be, you'll be tested on in your operating systems class. Similarly, I won't ask you about like the history of where threads came from with the idea of like the fork system call and that kind of stuff. You know, the focus would be on the concept of threads, how threads kind of work. I'm trying to think. I'm not a fan of memorizing code. So I would like, for instance, you know, I don't want you to go and memorize the syntax for creating a thread and, you know, the function thing for, you know, if we kind of go back in here and we go to MPC. Well, here's the MPC move, but it's really his come alive function where we create a thread. The thread has a target, which is the move function. And then we tell that thread to start. You know, if you wrote thread code, if I asked you to write thread code, as long as it was, you know, kind of in the spirit of this, that would be okay. I probably would just give you the code and tell you to write the function. So I might give you this and ask you to write the move function, for example, where the move function is effectively just logic. You know, sleep for 5 to 15 seconds, as long as we're currently allowed to move, figure out where we want to move, and then take the exit. That kind of thing. All right, not that theory is not important, but the things I'll test you on are things that are specific to computer programming, not necessarily to the underlying theory, unless the theory is directly linked to computer programming. In this case, threads and processes are more of an operating systems concept. Same thing with this. We talked about, you know, in that context, operating system attacks and things like that. You know, you might talk about this in the OS class and the cybersecurity class, not something I'm going to test you on in here. Okay, but this is where things get a little bit more rubber hits the road. I'm not going to ask you to tell me, you know, deep details about threads behind the scenes, but you should definitely understand that threads create another thread of execution that avoids blocking. Okay, so that gets us to everything post the midterm. So let me go back before that. First of all, there'll definitely be at least one conversion question on the exam, either a numeric conversion from, you know, binary to hexadecimal or something like that, or it could also be a size or speed question dealing with, you know, megabits to kilobytes, that kind of thing. So make sure you're aware of that stuff. Let's go through here and point out things from before the midterm that I think are extra important. So here's your conversion stuff. Make sure you review that. Definitely be familiar with modulo. You need to use it to write conversion stuff, but you know, that idea of something having an integer division, having a remainder versus the whole number result of integer division. And here's your bits versus bytes stuff. Everything's a scalar of 1024. I won't ask anything about specifics like high definition TV, like the actual resolution, that kind of stuff. I'll give you the information that you need. I probably won't ask you compiled versus interpreted on this exam. You've already been asked that. Certainly have an appreciation for object-oriented versus procedural, though. That's what we focused on since the midterm. The whole idea of memory, asking questions, repetition, that's how human beings solve problems. I probably won't ask you that directly, but you should indirectly understand that concept and you know, be able to create variables, be able to write if statements, you know, create Boolean expressions. I won't ask you anything about RESTful APIs. These things are covered in the 460 class more specifically. We talked about it in here in terms of computer programs communicating with each other. So kind of giving us a foundation for the types of environments we might be writing software in. Like in the 250 class right now, we're currently writing Android applications. So we're applying Java to the Android environment and seeing how that works. Certainly the concept of data representation languages, specifically JSON, and how it looks for our, kind of looks like our dictionaries. Maybe even the idea how we could represent our map for our game is a JSON object. History of languages, I don't really care about. I know we're out of time. I'm just kind of flipping through here pretty quickly. No bitwise stuff. Definitely be familiar with collections, lists, and dictionaries. Definitely with strings. You don't have to memorize some of these functions. I would expect you to know the find function. I would expect you to know the strip function. I would expect you to know the split function that we use today. Nothing with mutable versus immutable. So we never talked about tuples really. It's just like a list you can't change. Be able to do user input, but it's probably not overly important on the exam. Variable scope is important. Be able to write our different loops. Understand the difference between returning and printing. Understand the idea of variable passing, passed by value versus passed by reference. Okay, I think that pretty much covers the exam. So start looking through that before Wednesday. And if you have questions and you want me to go over any concept and write some sample code for it, I'm happy to do that. And then we'll talk about databases. Questions, comments, concerns, bribes? All right, I will see everybody on Thursday.